Good morning and good afternoon, everyone. Welcome to our second webinar of the year on hybrid modeling in oil and gas. Fantastic to see so many of you again, some returning from our previous webinar on production optimization and real-time monitoring, which in fact is available online also on demand. But let's get cracking immediately with the topic that we would like to introduce you to today, which is really the heart and soul we would like to talk about. We have an interesting agenda prepared for you. Originally, we will look into what hybrid modeling per se is, trying to define better for you the physics-based and data-driven modeling approach. We then will share with you our philosophy of why we are wanting to achieve a hybrid modeling approach, truly thinking that combining these two approaches will achieve the best of the two worlds. And lastly, of course, we will simplify this by showing you 3 use cases that we have been working on that will show you how we utilize then the hybrid approach to solve some of your challenges in your operations. A couple of words to us as a company for those that are not so familiar with us. We are a flow simulation software company based here in Oslo, Norway. Founded in 2017, so still very young. However, we have been market proven in the very short time. This is due to the fact that we have over 200 years accumulated flow simulation technology expertise, predominantly previously from SPT Group and then Schlumberger. But it's also because we have really developed our technology in close relations with key operators in the market. We can name here that our Flux virtual flow meter has been developed together with Petronas and our Flux stability advisor together with Aker BP. So for us, it's really about helping you to monitor your production real time and with that help you to optimize your production along any asset-wide KPIs that you yourself set as an operator. And maybe the uniqueness that we want to bring forward here in this world is we are striving for the most accurate quality data output, of course, for our clients. But equally so, we have listened to the market and we are realizing the accessibility of such software is really core focus for us to handle. We want to make sure that we can simplify the development and deployment for you to utilize software like ours. Integrate the software accordingly in your control room and also make it very low maintenance, which implies, of course, a certain cost efficiency attached to the software we have developed for you. So it is about the accuracy and the accessibility that we are working towards. And we believe that any operator in this world should be able to make use of flow simulation software in the market. Hence, why we have achieved to work with different international players over the short time, both offshore, onshore, both in the unconventional and conventional market. And what is truly the heart and soul, as I said, is our uniqueness in our hybrid approach, which is the topic of today's webinar. We are combining the predictive capabilities of physical models with the self-correcting abilities of machine learning. And here we have our 2 presenters that will really specify this now over the next 20 minutes. We will afterwards start with a discussion around the topic as well. And of course, we welcome any questions that you have. So do make use of the question box in your webinar tool. So let me introduce our 2 presenters. We have Johan Henriksen, our product portfolio manager here at Turbulent Flux, has been with us for 2 years and is the interlink between the technology and commercial department in-house. And secondly, we have Songshang Yang, our senior data scientist, been with Turbulent Flux for 3 years now and heading our machine learning department, obviously with that being an integral part in the development of our hybrid technology. So without further notice, I do leave the word then to Johan. Johan, the stage is yours.
Thank you very much, Julia. So a physicist and a data scientist on the topic of hybrid modeling in oil and gas. And here, really, the topic is about how physics and machine learning combined can deliver a value that is greater than they could do on their own. But first of all, if we look at this, if we talk about modeling, why are we doing modeling? Is modeling just a scientific tool where we understand how objects fall to the ground, why planets orbit the sun? Well, that's the scientific side of modeling, understanding the world around us. But we can then take this and we can bring it into an engineering perspective. We can take this and understand how do we erect buildings, how do we build bridges or construct cars so that they meet the standards that we set for them, that they are durable and that they fulfill the demands. Of course, if we move ahead, we look into our own domain, we look into oil and gas production. Of course, modeling then has a very broad applicability. It starts with finding the hydrocarbons, understanding the geology, understanding the geoscience, finding the reservoirs, but then understanding also how we drill the wells, how we complete them, and how we transport the hydrocarbons from the reservoir through to the processing facilities. But it's not only an engineering design aspect to modeling, because you can actually bring modeling into the control room as well. Looking at modeling as a tool that will help you to deliver and to operate in an optimal fashion. So we see here a broad applicability of modeling as such. So if we look at this now, if we start, then we can look into the physics side of things. And if we start with physics, physicists, like many scientists, like to speak the language of mathematics. We like expressing ourselves in equations, and we like to do so from the bottom up. We like to do this by first principles. We start out with a model, and we then use that model to describe what we see around us. So, but no matter how nice a model is, it needs to be predictive. It needs to predict what is going on around us. So we can then gather data and see if the model really predicts reality. And this is really where we need to also make a stand on the differences between first principles modeling and empiric models. Because we could start the other way around. We could have started with the data and then fit a model to that data. But more often than not, we then see that we get challenges when new data becomes available. And that is, a model to be useful needs to be predictive. So whenever we get new data, whether in the same area where we have data from before or outside, it needs to still be predictive. It needs to extrapolate outside the realm where it was first developed. So if we look at this, we turn toward oil and gas, we turn toward flowing pipelines. We can look at this Navier-Stokes momentum equation. It's a central part of how we do the modeling. It's a central part of any multi-phase flow simulator. But if we look at the pipeline on the left here, or if we look at the equation, we see that both of them exist in a three-dimensional reality, and then you add time to it. So in essence, a four-dimensional continuum. This is very nice because it's a universal way of looking at things, but it's also very challenging to solve. You can solve this, or many of the equations we have, you can solve for only a limited number of special cases. So in physics, what we need to do is then to introduce simplifications. And if we go to that and we look at how we go about this in pipeline modeling or pipe modeling, we say that the fluid is transported in the actual direction. So we can then simplify and say that we go from 3 spatial dimensions to 1. But still, this is not very practical if you want to use it and put this into computers. So what you do then is that you discretize your models, you make sure that they are fit for numerical modeling so that you can then introduce them into computer softwares that can deliver value and insights. And of course, what we see here is then the basis of what we have in our flux simulator, our in-house transient multi-phase flow simulator that underlies most of our solutions. So if we look at physics-based modeling as such, we can see it has benefits, but it also has challenges, of course. The benefits are that it is based in first principles. You have models that are predictive, and by that, they should be universal and you should need no data to set up these models. But given that we are doing simplifications, we're doing discretizations, some limited amount of data will still be required to validate the models we are applying. But of course, if you look at it, it is a complex world around us, and there's a big complexity in these models if you want to model every detail. In terms of that, you will need models and you need to understand every component. You may not do that. And also, since these are mathematical models, systems of equations that needs to be solved, you need to have sufficient data to solve for the unknowns you are interested in. So you need to have sufficient amounts of sensor data. And of course, with a complexity in looking at time-dependent models, it comes at a high computational cost. And by that, there could be other ways to tackle these problems, to address challenges in modeling.
Let's talk about machine learning. A very hyped buzzword in many areas. A study shows that the digital universe grew exponentially over the last decade. The data doubles its size every 3 years. And data has no value if we don't analyze it. Machine learning is a set of algorithms that can learn from the data and discover its underlying patterns. It has been used to master the game of Go, to predict the human protein folding. It can even help scientists to understand the most complicated particle detector at Large Hadron Collider. So, with the growth of data and its powerful algorithms, we can say that machine learning is the future. Okay, how we apply machine learning to build data-driven model at turbulent flux. First, we get the input data from our client's data platform, and we analyze the data. Here, we leverage our domain knowledge to build a system to verify the data efficiently, which means collaborations between data scientists, petroleum engineers, and physicists. We do the data cleaning and improve the quality. And then we apply machine learning algorithms to build the model. This is so-called data-centric approach. Once we build the model, together with our IT experts, we build data pipelines to make predictions and use it in many applications. This data pipelines has some benefits. It is very fast, they are very easy to deploy, and can be scaled to many wells. Of course, we have challenges, especially in the oil and gas industry. For example, some of the wells might have a short period of operation time, then we have low data volume. Some wells might have been run in optimized mode, and then we have small data variety. The data quality is a problem that we have faced in many cases. Also, the operator might change some equipment or the lifting method. This kind of change in operations will make the data model no longer accurate.
All right. So if we look at this, data quality, of course, can be a challenge for both physics and machine learning. And in terms of that, we already here see a touch point where the two domains can collaborate to resolve problems. But as a physicist, if I look at some of the challenges here on the machine learning side, we can look at the low data volume, so we can look at the data variety. What I immediately think is, but let's use simulations here. We can use simulations to extend the amount of data. If we have a small or narrow operating space, we can use simulations to span a bigger phase space and ensure that we have the variety we need. Further, if we look at the limited capabilities in terms of extrapolation, yet again, we can use physics to expand on those limits. So we can then gradually move outside the box of existing data. And of course, if we look in terms of non-stationary processes, if such a process would be detected by the machine learning, you could then hand it back over and let a physics-based simulator take over, looking at the transients and the time-dependent phenomena.
As Johan said, we can use machine learning to learn from the physics simulations, which means we can mimic physics by machine learning. And these fast predictions and scalability can help the physics model to meet in very time-demand scenarios. Furthermore, if the physics model needs some additional sensors, or there are some missing sensor values, we can use machine learning to use all the other available data to generate synthetic data. And also, the data quality is a common problem for both sides. Here we leverage our domain knowledge and try to tackle this problem.
So in terms of that, we have now looked at how we can use physics and machine learning to address problems in science and engineering. But what we argue here at Turbulent Flux is that the best is if we combine the two. We can use physics to leverage the machine learning, and we can use machine learning combined with the physics and merge this into a hybrid technology. But of course, in terms of that, it's all about putting it to the test. It's all about what you can do with this. And in terms of that, we're going to walk you through 3 use cases here showing different aspects of how we can apply hybrid modeling and how we use this to deploy solutions for our clients. So in terms of that, we can look at the first use case here, and this one is one case where we use physics to generate data and then support machine learning. The challenge here is that you have a tieback into a platform with slug flow. The challenge is that these operational slugs, they can cause operational upsets on the platform. So that means that you need to optimize your operations in such a way that you can maximize production without causing operational upsets. This could be tripping the separator by flooding it with liquids, or you could get a gas surge that would trip your compressor. The challenges here are, if we look at it in terms of a physics-based model, is that slugging is a stochastic phenomenon. It means it's not deterministic. You cannot say that the next slug is 4 minutes out and it will be of this size. So you need to tackle this by statistical approaches, and by that, analytics and machine learning would be a good choice. The challenge is only that the amount of data available is too small for this to cater for a machine learning approach. So the way we go about this is that we use simulations to span the phase space and then create the data required to create an analytics-based solution for this operator. So this solution is called the Flux Stability Advisor. It's a solution we have developed together with Aker BP, and it was presented at ATCE last year. So we use simulations to generate the data and span the phase space, and then we use analytics to generate the insights and to understand the likelihood for instabilities in the flow, and also understand the risk of these instabilities creating an operational upset. What you see here on the right-hand side is a snapshot of the dashboard that we have made available for Aker BP for this one. And you see here the likelihood for slugging in red. Not all of that slugging is, however, damaging to your operations, and you can live with some of it. And the question then is, how do you compare, and does this add value? And if we look at this using these measures, they can be generated either by simulations or based on real data. And what this one shows here is actually a comparison between the calculated risk from our solution and the one done in retrospect using data. So what we can see here is that we can very well assess the risk, and by that, when the operator uses this, they can understand how to operate their asset in a safe manner, and if they are approaching intolerable conditions, it will give them insights on how to move into safer operations while still optimizing their production.
Let's look at the use case that we apply machine learning to support physics. Here, we deliver three-phase flow rates to an operator insights into daily production on a mature offshore field. Our physics simulator Flux VFM can predict the three flow rates based on the pressure and temperature sensors at downhole, upstream, and downstream. And the challenge in this case is that some of the wells does not have a functional downhole sensor, which is needed for the physics simulator. The solution to this challenge is by looking at the other wells with full sensors. We apply machine learning on the data from these wells to build a model that to predict the missing value for this well. And this technique is called transfer learning. In the transfer learning, we need to study the properties of the wells carefully. Here, this plot shows feature 1 versus feature 2 of 19 wells. And we can clearly see that these wells follow into different groups. Let's say if the orange well does not have a downhole sensor, we use the green and gray wells to build a model to predict the downhole sensor for this orange well. If the yellow well does not have downhole sensor, we chose the blue and purple wells. Once the model is built, we will verify the model among the wells, and we can also verify the model in our physics simulator. And this is very important. With the synthetic downhole sensor, our Flux VFM can generate 3 flow rates in real time. Here is an example of the daily oil predictions in green line versus the measurements. They are in very good agreement. Okay, another use case that we apply physics to improve machine learning and come back again. Here the objective is to provide 3-phase well flow rates to an operator in unconventional spaces to reduce the frequency of well testing. Again, our Flux VFM will predict the rates based on these sensors, but the challenge in this case is that the choke is always full open. The pressure drop across the choke is too small so that our physics model cannot determine the oil and water split accurately, which is the water cut here. However, our physics simulator can predict the gas and the liquid rates at a very good level. But our clients really want to see the oil and water rates separately. Okay, can machine learning to help this challenge? The answer is yes. We use machine learning to build a model to predict the water cut. And during the model building, we found that we can apply some physics models to do feature engineering. For example, the choke model and tube model. We extract more meaningful features to be the inputs in our machine learning model. And this approach will significantly improve the machine learning model in performance. And here is the example of our water cut predictions versus measurements. They are in very good agreement. Once we have the machine learning model, we can finally combine all of them together. So we fit the machine learning output into our Flux VFM, and then we can generate all 3 flow rates. Here we can see the water and the oil rates separately. Here we can see that we predict the water breach even before the well tests.
So if we look at this, we've now seen physics, we've seen machine learning, and we need to realize that while these are separate in domains, we need to tear down the wall between them and not address them as two separate topics, but we should actually look at them and see how we can create hybrid solutions combining the two. But if we look at this, there's actually a sliding scale. There's not just physics, machine learning, and hybrid. If we look at these 3 use cases that we just gone through, we can see that they fall in different areas of this map. If we look at the first use case, we used physics to support machine learning. So it was heavy on the machine learning. The physics did some of the heavy lifting beforehand. If we look at the second use case instead, we had the physics simulator, our Flux simulator was the core component of the solution, but we then used machine learning to provide additional inputs. But in terms of that, if we look at the third use case here, that's where we see the really true value, and that is what we call a true hybrid. It is a solution where physics and machine learning mutually benefit from each other. having a symbiotic relationship between the two and leveraging each other. So by that, we have come to the close of this webinar, and we would like to thank you for your attention.
Yes, and first of all, thank you both to Johan and Songchang for this very insightful presentation. We have a few minutes spare to do a bit of discussions, and again, do not hesitate to bring up any questions. We will, of course, attend to them as well. But can I leave the word a bit to you both, Johan and Songchang? We talked about data availability, data quality quite a bit in our modeling approach. Johan, maybe a question addressed to you. What sensor data configurations should we ideally have available?
Thank you, Julia, and thanks for a good question there. And it's a challenging question to answer because it really depends. It depends on the system and it depends on what is available. If we look at the wells here, the VFMs that Songchang demonstrated in the use cases, we are often working with downhole sensors, wellhead sensors, and then a pressure drop over the choke. And those are sufficient for us to resolve the three-phase flow rate. So typically 3 delta pressures and delta temperatures together will help us resolve that. If that is not available, of course, we can utilize any other sensor that exists in the system or even further downstream. So it's really a case-by-case discussion here because we know that all assets are different and there's not one silver bullet solving it all. But at the same time, we also see here, and I would let Songchang elaborate a bit on that one, because we see here also that we can then leverage machine learning to help supply data for the physics. So Songchang, if you would like to elaborate some, I think that would be a good thing.
Yes, it really depends on case by case. For the missing sensors, we need to look at all the other available data and also maybe other wells together to build a model.
Right, and maybe to expand on it, data availability, data quality. You did mention both that it's a challenge for both modeling approaches. So how do we overcome this challenge at Turbulent Flux? Songchang, maybe you can start off here.
Yes, the data quality is a common challenge on both sides. We need to look at data carefully, and we heavily leverage our domain knowledge to verify the data. The data volume and also the data variety.
So you basically say, okay, data volume, data variety, and the domain knowledge is key here. Johan, coming from the physics-based background, would you then go that far to say that the domain knowledge really remains vital for the modeling in oil and gas?
Yeah, I would truly say so, and I truly believe it, because if you would step away from the domain knowledge and assume that you magically would get results from some black box, I think you're taking a very big risk. And I think the big challenge here is to understand what is sensible input data to these systems and understand that. And that is, as Songchang says, where you can leverage a lot of the domain knowledge, but also when it comes to the outputs and incorporating that into the solutions in such a way that the solutions are also self-sufficient, incorporating then the domain knowledge so that the models themselves can do some quality assurance, raise alarms if they see that things are going astray. So adding that bit of smartness there is really where I see domain knowledge adding value to these solutions.
And maybe one more questions we have here that we also got in our previous webinar. Johan, you did mention the Flux simulator. Can you expand on our simulator and how it's applied to our solutions?
Yes, of course. Thanks for that question. So in terms of that, I mean, our foundation technology is the flux simulator on the one side. It's the optimizations that we apply through our flux optimizer, and of course then the flux analytics, which Songchang has talked about. All of this is developed in-house by us. We're not depending on any third-party components here. And if we look at the simulator specifically, it is our own in-house transient multi-phase flow simulator. And the way, since we are looking at the operation space, we are looking at producing assets, the key here is to ensure that we have a solution that is fit for purpose and ready for real-time deployment. So that's really the key for the simulator.
Right. So I think we are running a bit out of time here. We got a lot of questions in, so thank you to the audience for bringing it up. We will, as I said, attend to them, of course, in quick time. And also, of course, we were in 30 minutes only able to showcase here now 3 use cases from the offshore and unconventional world. We are very keen and happy to discuss other use cases and also understand your challenges better and show you how we can equip you with the insight on flow and in order to help you optimize your productions. So I will have to close this webinar now due to time, but I thank you all very much for joining today. The webinar will be made available as a recording to you. And of course, many thanks here to our presenters, Johan and Songchang. So with that, I wish you all a very good remaining day, and we hope to see you at one of our next webinars. Thank you.
Thank you.
Thank you.